to the third day of BARC Basic Astronomy Workshop 2021, and today is the last day for this workshop. So সবাইকে আবারও স্বাগতম জানাচ্ছি এবং আজকে আমাদের শেষ তিনটি লেকচার হবে, আজকে শেষ দিন। সো হোপফুলি আজকে তিনটি লেকচারেই তিনজন কিন্তু ইন্টারন্যাশনাল ইনস্ট্রাক্টরস থাকছেন এবং তারা তোমাদের ক্লাস নেবে। সো আই বিলিভ যে তোমরা তোমাদের কোয়েশ্চেন্স রেডি করে রেখেছো এন্ড তোমরা তোমাদের যত কোয়েশ্চেন্স আছে সেগুলো তোমরা করবে। অলরেডি উই হ্যাভ অ্যান ইনস্ট্রাক্টর, Zaif, right? If I'm not wrong. Okay, so
Jeff. Yes, Jeff.
yeah, I want to introduce you at first. Basically, Mr. Zaif is an atmospheric and computer scientist over a decade of experience imaging deep sky, and he does a lot of astro images or image processing through space data. And right, Zaif, if I'm not wrong. Yeah, so we have already done a webinar on astro image processing and space data calibration, right? So Zaif আজকে তোমাদেরকে আবারও সেই জিনিসগুলো দেখাবে, শেখাবে কিভাবে স্পেসের ডেটাগুলো ক্যালিব্রেট করতে হয়, এন্ড সেখান থেকে আমি যে গতকালকে তোমাদের দেখিয়েছিলাম ইমেজ প্রসেস করা, সেগুলো কিভাবে করতে হয় Zaif তোমাদেরকে আজকে শেখাবে এই আজকের ক্লাসের মাধ্যমে। সো আশা করি সবাই মনোযোগ দিয়ে ক্লাসটা করবে এবং তোমাদের যদি কোনো কোয়েশ্চেন্স থাকে যে কিভাবে ইমেজ প্রসেস করে অর কি কি জিনিসপত্র ইউজ করা হয়, you guys can ask to your instructor and he'll reply you as soon as possible. Okay, so সবাই অলমোস্ট চলে এসেছে I think, and আমি আর লেট করব না। So Zaif, yeah, you can start your presentation. I'm giving that permission even.
Okay, great. Thank you so much, Rifat.
Thank you.
So thanks everyone who is attending, and hello to my friends and family that may be connected. As Rifat mentioned, I'm kind of far away from you guys. It's 2 a.m. here. I'm in Las Cruces, New Mexico in the United States, near El Paso, Texas, if you know where El Paso, Texas is. So I am going to go ahead and share my screen.
Okay, I want to say something. Give me 2 seconds. Okay, so তোমাদের অ্যাটেন্ডেন্সটা আজকে আমরা এই লেকচারের শেষে নিব। সো কেউ লেকচার শেষ হলে চলে যেও না, ওকে, লিভ নিও না, তোমরা থাকো এবং তোমাদের এই লেকচারটা শেষ হওয়ার পর তোমাদের অ্যাটেন্ডেন্সটা নেওয়া হবে। ওকে, ক্যারি অন।
Roger. Okay, I'm going to try to share the presentation and see if I can get started. Better view here. How does that look? Are you seeing it okay?
Yeah, it's okay. We're seeing the presentation.
Great. Shrink this window down. And I will get started again. Okay. Yes, so I go by Jeff. There's my full name, Jeffrey O. Johnson. I have some contact info there if anyone needs to have some follow-up questions following the briefing here today or tonight, depending on where you are. And all the images that you see in this are from myself. I captured the data and created the images from data that I collected, including the background that you see here on this opening slide. And this image as well, and I have in the bottom left, you can see the details on the image. So just to give some background, since I was a boy, I've really loved astronomy. And so as I got into really my, since 10 years old and then into my teenage years, I wanted to kind of get closer to what is out there. So as I became an adult, I work now as a professional atmospheric research scientist. So in effect, I study planetary atmospheres. The planet just happens to be planet Earth. So I love this career, and for the hobby of astronomy, I love astronomy so much because it, together with the interest of what is out there, it brings use of technology, hardware and software, where I even write my own code to control the imaging. I'll talk about that a little later. So here's some information about me. I was actually born in Germany, a military brat, as they say. So my dad was in the service when we lived in Germany. Um, Both of my parents are U.S. citizens. So we moved around a lot while my dad was in the service, and you can see the different states in the United States that I lived in: Texas, Colorado, Nebraska, Maine, Idaho. I'm one half Norwegian and one half Austrian. My dad was full Norwegian, and my mom is is full Austrian. So I moved to Las Cruces, attended New Mexico State University. Actually, I started in engineering and physics in Boise, Idaho, before moving to New Mexico. So there's my background on education: Master of Science in Engineering and Bachelor's in Geography with a minor in Meteorology. So again, my career is research, atmospheric and computer scientist, and earlier career information there, including operations research as well as research meteorology. So my hobbies there at the very bottom: astronomy, of course, that we'll hear about today, computer programming, bodybuilding, martial arts, and music. So going back to where I started, a book that my dad gave me was simply called Astronomy, and he gave it to me when I was 10 years old, and I just really fell in love with it since that time with astronomy. Back in 1996, I used a film camera to take a picture of comet Hyakutake, which you can see in the top right there. Not a great image, or photo, but it was fun. Later, I bought a 10-inch Dobsonian just for viewing. The next thing I know, I'm trying to take pictures of what I see through the lens. And so there's a couple examples there of Mars and Saturn back in 2003 and 2004. Some years later, I bought an SCT telescope, and that was in 2005. I bought it purposely for imaging. So you can see the difference, the result in Saturn that you see here. That was a year later. And I have the details of how I took that image there as part of this picture. So I loved planetary, but I loved deep sky even more. So first thing I did was, okay, let me test the same setup that I used for Saturn with deep sky. This is the result. Definitely not great. Humble beginnings. This is M42 Orion. And, just basically taking a picture through the eyepiece. But it kind of spurred my interest to figure out, okay, how do I and what do I need to do to get more into deep sky imaging? So again, this was about 15 years ago. Yes, 2006, January. So 9 years later, here's the same object that we saw on the previous slide. So there's Orion M42. And it's a smaller telescope, and it's just a different kind of a camera and different equipment. Key equipment that I mentioned there is a mount. So, the size of the telescope, it depends which one you want to use, depending on what kind of an object you're trying to capture. In this case, a very small telescope compared to the one we saw on the previous slide with a 10-inch reflector. This is only a 2.4-inch refractor telescope, so much smaller. But again, there's a lot to this on decisions on how to capture images and data. So as I mentioned here, large differences in equipment and techniques for planetary versus deep sky. So I won't go into any more detail than that in this talk. So now I will jump into data collection and calibration for deep sky space data. Here are the two telescopes that I'm using currently. The one on the left is a 130 millimeter refractor. The one on the right is the one that we just saw the previous image from. That's the 2.4-inch or 60 millimeter refractor. And it is a special astronomy CCD camera on the back. It's not your regular DSLR or point and shoot camera. This is very specialized. It's a cooled CD camera, and I'll talk a little bit more about that in the following slides. The one for smaller, kind of distant objects, my favorite is actually galaxies. The large telescope on the left is what I use for that. For a wider field targets or a wider view, that's the smaller telescope on the right. And for me, excuse me, I have a portable setup. It takes some time, but I set up and I take down every night, and then I am out. And I'm planning to build an observatory to kind of mitigate that somewhat. So setup normally takes about 1 hour. So the general setup, I will choose either the larger or the smaller telescope we saw on the previous slide. A mount, which was in both of those pictures, is a Takahashi EM200 mount. It's a German equatorial mount. And the camera is a QSI, Quantum Scientific Imaging, is what QSI stands for. And the particular model, 690 WSG. So it has an internal filter wheel and an integrated OAG, or off-axis guider port. And if you look at that image, you see kind of that tube on the top. That's another camera, an off-axis guider camera called the Lodestar.
I have a question. I have a question.
Oh, sure.
Yeah, Takahashi, isn't it a Japanese product or?
Yes, it is Japanese. That's
okay.
right.
Thank you.
Sure. So both telescopes and the mount are from Takahashi. They are exceptional as far as for imaging. They're kind of famous around the world for their quality. It's just fantastic. I got the mount and both telescopes at the same time because I did a bunch of research before I purchased those. And they have not let me down. I'm very, very impressed. It's super, just incredible quality. Okay. And here are the two telescopes, one sort of on top of the other, so you can get a difference, see a difference in size. The bottom, the large one, that's 5-inch or 130 millimeter refractor, and then the smaller 60 millimeter refractor above it. Just again for a size comparison. That refractor, when you think 130 millimeter or 5-inch aperture, you think, it's not very large, but that refractor, the way that the optics work, it's a very large telescope. So, okay. So I'm not going to go through in too much detail because I don't want to spend too much time, but effectively the setup, as I talked about earlier, that takes about an hour. I'm going to step through it here. First on the list is balancing the scope using counterweights. Second is polar aligning it using Polaris. And it's by the year, month, day, hour, and even the minute using standard time. And that helps the mount kind of orient itself, if you will. And for Takahashi, I have a list there, or a mention there on number 3 about you have to adjust it based on what your what your longitude is. And then there is a bubble level that you have to center. And a list of cables and power. And I have a little image there on the left of there's 3 USB ports that I'm using. One is for actually both cameras. The main camera plus the off-axis guider camera are coupled into one USB signal. Then there is a USB port plug for the mount and one for the focuser. And I use a laptop that you can see there in the picture. It's actually quite old laptop, more than 10 years old now, and it's my workhorse. It's really has done very well. And a lot of cables, so you can see them there. Again, since it's portable and I set it up at night, so several cables coming from the camera and one from the motorized focuser, which is sort of in front of the camera. You see, let's see if my arrow works. I don't know if you can see my arrow pointing, but right there, that's a motorized focuser. And so on the left is the control box that's part of the mount. And so it has power input, hand control box input, RS-232 port, and an auto guider port. RS-232 is basically a serial cable that I convert to USB, and then that is controlled through different drivers on the computer. And that's what's controlling the telescope mount. The mount, again, is just fantastic. And as are the telescopes. And here's kind of the back end of the large refractor, the TOA 130 millimeter. And so all I want to point out here is you see I have the different adapters. One is a flattener. The one at the front, it says TOA 67FL. That's a field flattener. And then there's some spacers, and there's other stuff and other stuff. And each one of those I have listed 22.5 millimeters, 17 millimeters, 18 millimeters. That all means something, because at the end, if you look on the right side, 106.5 millimeters total back focus. If you do not get the correct distance behind a refractor, it will never come into focus. So that's where refractors are different from reflectors, for example. So any further details on this, please contact me separately. But it just gives you a feel that there's a lot involved just to be able to get a telescope is like this, to get into focus. Can we finally start imaging after going through all of that? No, we're not done yet. So we have to orient them out. And normally you do that by finding three known stars or objects, basically triangulation, and try to find them in different parts of the sky. And it will help then to orient them out to find different objects. And on the left, I created this go-to database with the right ascension and declination coordinates that you see listed there in columns for each of these objects. So that's a file that I actually reference when I am orienting the mount. Then once you get to the object that you want to image, you check and set the focus, verify which side of the celestial meridian you're on, because that matters on the guiding for the guide commands that come from the off-axis guiding camera to the guiding software. Then you find a guide star, and finally, you can start imaging. And there's some code I wrote. It is a script. I'll show an example of it here later. That helps, that does control the camera exposure times and the filter wheel. So for the data collection and controlling the mount, this is the software package I use. It's called AstroArt, and it's version 5.0. I think they're up to version 7 now, but I am not interested in upgrading because this works very well for me, the one that I'm using currently. So I mentioned about focusing, and so I have some notes here that I wrote to myself about what to do to get proper focus. It's just an image. For my own kind of library, if you will, I will have images or text files or data files to sort of reminders if in case I haven't gotten out for a while or something. It's just a reference to, okay, this is what I have to do to set something up, etc. So on the screen, the larger image there, finding a guide star. And here, that small little dot that has the rectangle around it, that's a guide star. And that is the guider camera, the off-axis guider camera is picking that up. And they call it off-axis because there is the main axis of the main telescope. And this picks up an outer part of that field of view, if you will. That's where the camera is looking. There is a prism that is going down, and before it gets down from the top of that camera, and it does not interfere with the CCD chip's image data, but it's just above it. So this camera is looking down the same optical train as the main camera. So it works great for tracking. So you find this guide star, as you can see in that example, the guide window, and there it is blown up. And then you click on, it says mark guide star there. You probably can't see it very clearly, but that's where you click, and then it starts guiding. So here's the code or software. It's basically a variation of BASIC that the AstroArt 5 requires for writing your own scripts, and so it's pretty straightforward. They're very clean, and I actually have sets of these, or I can modify them on the fly when I'm out in the backyard with the telescope for basically looping through the different filters. And you can see an example I have here for H alpha, as well as the luminance, the red, the green, and the blue, or in other words, HLRGB. And in the script, you see a C, that's referencing the clear filter, which is the same as luminance. But that just shows you an example of what the script would look like. So now we can finally start collecting data. Excuse me. And so here is what it looks like when data is being collected in the backyard with the large telescope, the 130 millimeter, using Astro-Arc 5 software. However, this is my view from inside the house. If you can see kind of the larger outer screen, and that's back when I was using XP for the inside house. So this is an old image, but so inside the house, and then I use the VNC viewer to look at or connect to the laptop in the backyard. And so you see the inserted or embedded screen of the backyard laptop. So it's nice when it's cold outside and you don't want to sit out there with the laptop the whole time. So you can kind of keep an eye on things as it's collecting data. And the image here is a single 10-minute exposure in H alpha. It was that came through the camera, and that shows up on the screen, and then it cycles to the next image. And you can see above where that guide window is, you see 600, so that's 600 seconds. So it's exposing whatever percentage that is, over 50%. It's exposing the for the next frame of 10 minutes. So now I want to get, after we have collected the data, then we go to data calibration. Let's say we were out there all night, we collected 8 hours of data, and we've got a bunch of luminance and H alpha and RGB frames that we're ready to process to try to create an image. So we do data calibration. These calibration frames are used to correct artifacts from optics, as well as artifacts from the camera or the chip on the camera. For example, hot pixels or banding, etc. Because there is no perfect optical train, and there is no perfect camera, there's no perfect CCD chip. So calibration is used to remove these artifacts. Why that matters, and I have an example there. On the left is a calibrated image of M51, and on the right you see uncalibrated. So you can see a lot of this, I don't know, foggy, messy looking stuff in there, and that's artifacts from the optical train and or the camera itself. So what I use for the calibration frames when I'm calibrating the data, I use all of these that are listed: bias, darks, flats, and flat darks. And I talk about, here in detail about what each of those are, but effectively, the two, they're all important, okay? So I use all of them. But the darks are the ones you've probably heard of before, and the exposure and the temperature must match what the light frame was. So if you collected data, let's say it's 10 minutes long for a luminance exposure, well, you've got to have a matching dark frame for 10 minutes. And it has to be at the same temperature. And when I'm talking temperature, this camera allows you to actually set it at a certain temperature, and it's normally a delta below what the ambient temperature is. It can go to some maximum. And for me, just because of the weather we have around here, in the summer it gets fairly warm even at night. So for me, I will set it, the two different temperatures I set are -15°C during the winter months and -10°C during the summer months. And flats are very important. The next one after dark. Those are, you need a flat for each light filter. So for all of those filters, L, RGB, and H alpha, you need a flat for each of the filters. And if you move the camera or change telescopes, you need a new set of flats. What's nice about darks is you can create a library because it's just tied to the camera. but the flats are tied to the camera coupled with the telescope. So, and then flat darks are similar to the flats for the luminance frames. Okay. So now here's some examples of what the frames look like. These are from my library. And all of these were used for what I'm going to show later, the Andromeda Galaxy, or M31, shown in a later slide, and was using the small 60mm scope. Here's an example of bias frame, not real exciting. It's a stack of 10, which I normally do, and it's at a set temperature, and here's the exposure as fast as the camera can expose, and that's the minimum exposure that this camera will do, 0.001 seconds. Here's a dark frame, a stack of 10 5-minute exposures at -10°C. I mentioned has to match the light frames, which for Andromeda Galaxy, I was using 5-minute light frames. And the temperature was, for the CCD, was set at -10°C. Here's an example of a flat frame, so you can see. Yeah, I mean, honestly, Takahashi has probably one of the, if not the best optics in the world. I mean, their optics are fantastic, but even with, near perfect optical train, you're still going to have some stuff that looks like this. And you can see it's, slightly vignetted. Even with using a very high-end field flattener, you're still going to have imperfections. I mean, the world is not perfect. So for this, you use what's called the light box. And actually, I built my own light box. And so you'll see here exactly how you take a flat frame. Okay, this is a light box. I built this 11 years ago, or 10 years ago. I think it was December 2010, so 10 years ago. I built this myself after reading up on light boxes, and I made it so this could handle up to, I believe, a 9-inch aperture. So it works with both of my scopes, no problem. Because back then, I had an 8-inch reflector, and I since sold to upgrade to the Takahashi. And there's what it looks like when you're taking a flat frame. So it's just like you're in the backyard imaging, except you're just pointing it at this light box. And you take fairly fast exposure. And what it's doing, it's the light box is providing a kind of continuous light source, and it's not varying if you design it right. And so this can then, a short exposure then, will help to sort of identify the artifacts, if you will, in that optical train, like we saw in that exposure that was from this. And the last is a flat dark frame. Again, similar to flat files for lights, you have a flat file for darks. And so it's very relatively short exposure. And it's covered because it's for a dark frame. So it's not exposed to any light. So using these calibration frames in the AstroArt 5.0 preprocessor, and that's what I'll go through now. So if you have AstroArt open, up there I have just a single luminance frame that you see in the background. And so from their tools, you select the preprocessor. And once that comes up, it's preprocessing window. You will see there that it's showing you what it has available. And so what I've done here is I selected all the light frames that I had for Andromeda, including the one that's in the background there, plus the others. I think I had 25 total. So we'll see here in the next slide. I can't remember. And then you select a bias frame. So the bias frames that I had also collected that I showed you an example of, I create a master bias, which is the stack of 10, and I put it there. And next is the, are those the dark frames? It's hard for me to even read. Yeah, the dark frames. So similar to the bias, I actually took an average there, or a mean of the sigma mean of the dark frames, and then I have the result there. Fill in the next one, which is the flat dark frames, yes. And then last but certainly not least, the flat fields. In all of those cases, again, they are averages of 10 frames each, as I described on the earlier slide. So at this point, you can go through the second tab of options there. And there's things to select. Again, I'm not sure how clear it is for you all. It's not very clear for me here, but effectively it's what kind of averaging do you want to do? Sometimes you want to actually do sigma averaging. It depends, and there's, that's beyond the scope of this discussion, but just to know that it's there. And what kind of stacking, normally I'll use star pattern to stack, these 25 frames, and software will do it for you. Way back in long time ago, when I first was getting into this, more than 10 years ago, I was messing around with doing manual stacking, and that got old pretty fast. That's before I had some good software that would do the stacking like Astro does. So you click the OK button, and it starts stacking, and you can see there sort of the small window there in front of the image says 2 of 25. So it's basically cycling through. And so you wait for that to complete. Once it does, then it's going to give you a final result, an unnamed final file of the stacked images averaged. So basically what you're doing when you're stacking is increasing the signal to noise ratio, which is what you want. You want to eliminate noise. And so for each frame, if you just have one frame, it's going to have noise from whatever. A lot of background noise just from, noisy data. And so when you average, then when you have more than one frame, it will start to show you what the real signal is back there. We want to get the photons that are coming from Andromeda and and other things. So the real data. So when you average, that's basically what it's doing. So here's the final result when you open it up, just in any image viewer. It really doesn't look like much, but the data are there, as we can see in the next slide. Just did a quick adjustment of levels only in Photoshop in this case. I actually use PixInsight as well, quite a bit, in fact. Photoshop I use to stack the layers of, once I create and I didn't go through here, but use RGB and you create an RGB, basically a color image, and then you have the luminance data and you can stack the luminance with the RGB. You can use either PixInsight or Photoshop to do that. So we see the data, and there's further data processing, noise reduction, levels, curves. I was talking a little bit about it, but the whole time as you're doing this, you pay close attention to the histogram. You don't, you can certainly look at the picture or the image, but you have to pay attention to the data, because that's what we want. We want to see what is really out there. And by paying attention to the histogram, you are not, you can avoid clipping the data, as they call it, which means cutting out data that's there and you didn't know it, because your eyes aren't going to see it necessarily. As we saw in the previous example, we didn't see much, but then once we adjusted the levels, hey, there's a lot of cool galaxy stuff back there. But getting into these further steps of data processing are beyond the scope of this talk. However, I'll show the final result. And so there's the final result of 25 luminance frames, and I think 5 each of RGB. There's no H alpha and there's no narrow band. It's just completely, excuse me, completely regular, if you will, visible spectrum, not narrow band. Although narrowband is part of the visible spectrum, however, it's an extreme end of it. So, and again, that's beyond the scope of this talk. And I have detailed information on my site, on my website, and here is the breakdown of that. The telescope that was used, the mount, the camera, exposures. You can see this where I have settings, and then the date and location. All right. So now I'll just go through some of my favorite images. Some of my stuff has been published by Yahoo News. Even in England, I saw the Yahoo News, actually Ireland, if you see it on the left, UK and Ireland. So it's pretty cool when you get some of your stuff recognized. It was pretty exciting. And so that has happened. And also in different magazines, Sky and Telescope and Astronomy magazine. So printed versus just, on the internet is great. Being printed in a hard copy is pretty neat. So, and yeah, probably the pinnacle for me in this very serious hobby of mine is in 2015. I made a discovery of a previously undocumented emission nebula, and I published the discovery. So it's something that I contacted professional astronomers to verify that this nebula had never been logged before, and it's in the area of Puppets. And so found it sort of on accident. I was using H alpha because I wanted to see if there is any H2 regions, as they call them, in that area, and it looked like there weren't. And then I picked something up, and first I thought it could have been an optical artifact. But after I processed the data, I realized there's something there. And the professional astronomer who logs nebula into catalogs, he verified that. It was pretty awesome. So, I mean, it's not going to get my name or anything because it's just an emission nebula, but still, it was fun. And so I'll just go through a few of my favorite images that I have. I collected the data and did all the processing on, and these are all from my backyard with the portable setups that you saw in the previous slide. So there's M33, Triangulum Galaxy. And there's Comet Lovejoy, C2014. And so I think I imaged that in January of 2015. Terry Lovejoy discovered it in 2014. That's how it gets its designation. And there's the Cone Nebula and surroundings. I was using the small 60mm refractor for that. And there's the Sculptor Galaxy, one of my favorites, and I actually want to revisit that. And this was there wasn't very much data in this for this effort, and so it was a very, very excellent clear skies night. And for this, I had to actually wait until it went behind my neighbor's tree, and I had to wait for it to get out from behind my neighbor's tree, and then collect some data, and then I was behind the other neighbor's tree. So there's all these challenges that you have in this awesome hobby. And this is the Rosette Nebula. And it's the first and last time I ever imaged this Rosette Nebula. I intend to go back someday, but I just haven't. This was using the small FS60C Takahashi refractor. And M45 Pleiades. And I think, I still have some more. All right. And this is the Pelican Nebula, IC5070. And that's using a lot of H alpha data because where I used to live, where I live now, there's not so much light pollution. Same city, but I built a house outside of the city center on purpose to be in dark skies. But when I captured this image, I was in the very bright sky, Bortle level 7 or 6 to 7, I believe, pretty bad. So you use H alpha, narrowband, which sort of filters out, if you will, some of the city light. And this is one of my favorites. It's called the Boogeyman Nebula. You can see the guy in there. It's LDN 1622. And Elephant's Trunk Nebula. You've probably seen some of these. The Boogeyman, maybe not, but this one's kind of famous. And a Dumbbell Nebula, M27. Eastern Veil, NGC 6995, and that was using H alpha narrowband, certainly for this one, and this one as well, using H alpha narrowband combined with LRGB in both cases, the previous and this one. And Horsehead Nebula, combination of narrowband and LRGB. And that's it. So as my ending slide is 2:30 in the morning. What are you doing? And that's me in the backyard with my telescope at 2:30 in the morning. And normally I'm pretty much out there the whole night. And when I take everything in at around 6 in the morning, then first thing I do is take it inside, make sure it's safe, and then go straight to bed. And that's it. And thank you very much for your time. And I'm ready for any questions.
Okay, কেউ যদি আনমিউট করে থাকেন প্লিজ মিউট করেন, আমরা কোয়েশ্চেন আনসার সেশনটা করব এখন। Thank you so much, my friend, for this amazing presentation, and I always feel good when I see your work, and I do follow your work as well. Even it's a great pleasure to work in this kind of image process because I do every night this kind of stuff, so it's really amazing. Awesome. Yeah, and everyone is praising your work, like Rehnuma Rai and awesome sir. Faisal, it's a very amazing pictures. Okay, Hassani, it's a very good. So yeah, everyone is liking your work. So do you have any kind of questions, guys? তোমরা unmute করতে পারো, আর যদি unmute করতে না চাও, then you guys can text here. আমি তোমাদের questions গুলো বলবো. So already কিছু questions এসেছে, আমি একটু বলে দিই. We have some questions regarding this image process. So Faisal is asking to you which programming language you used for this kind of image process.
Yep, the one that controls the camera is using a variation on BASIC. It's AstroArt came up with their own syntax, if you will, but it's very much just like basic programming language. So that's what I use for the camera, controlling the mount for the telescope.
Okay. Another question from, let me check that out. Okay, Srinjoy Dhar Dhruvo is asking, what does it means by 130 millimeter refractor or 60 millimeter diffractor?
Oh, yeah, sorry, I should have been more clear. That is the diameter of the aperture. So the 60 millimeter is something like that. So the front of the telescope, the aperture, and the 130 millimeter is something like that. And so it's just how big the aperture is that lets the light into the front of the telescope.
Okay. So তোমাদের questions গুলো তোমরা কিন্তু টেক্সটে দিতে পারো অথবা আনমিউট করে বলতে পারো. So do you have any kind of questions, guys? Okay, Hafsa Fariha is asking, why does frames need to be dark corrected?
Yeah, if the dark correction is primarily because of the CCD, the camera and the CCD chip. A really good example is, let's say you have a DSLR camera, and have you ever taken a very long, like a 30-second exposure, and then you look at the result from that and you see all these little red dots, all those red pixels, those are called hot pixels. And so when you're doing exposures, some of my exposures go up to 20 minutes long. And so that's the longest I have done. So you can imagine 20 minutes of exposure. Even with a cooled CCD, you're still going to get hot pixels. And so the dark frame, when you collect a group of dark frames, the hot pixels are normally fairly consistent on their position in that array. And so when you subtract the dark frame, you're going to remove those hot pixels from your image. And it basically gets rid of where there are, sort of bad pixels. There's other things as well for the dark frame correction that in addition to the hot pixels, for example, some of the banding that can occur from a CCD chip, and also other types of artifacts that are introduced.
Well, Shukorna Bonik is asking, how do astronomers collect data from the age of the universe?
Yeah, I love that stuff. So what they have to do is they use known properties of light, for example, and also known properties of different compositions. So if you have a very distant galaxy, There's called, the red shift, which is, how fast that galaxy is moving away from us, for example. And so they use kind of a combination of things to determine what the approximate distance is to these objects. And that's why if you look at any of these objects, there's always like plus or minus, 1 billion light years or something, because the more distance they get, the less precise it's going to be. So they use, yeah, I guess summarizing, they use a combination of different physical characteristics and known properties of physics and of space to determine those distances. It's not something that you can, just, do like you do here on Earth, like radar or something like that. Because if you're going to do that, you're going to have to wait 4 billion years for that signal to come back, for example. So.
Well, Shantam Ferdin Nabi, what are the best ways to learn astroimaging?
Oh, the way I did it was a difficult way. I kind of did it by trial and error. But a nice way is to get involved with different groups. And if you're just starting, there's certainly groups on Facebook. I'm a member of some of those groups. Find a mentor. When I started to get serious into imaging, there is a person who I worked with, and he was sort of my mentor on it. And he actually has made, I think, 10 or 12 asteroid discoveries. He named one of the asteroids after his wife. And I was like, okay, this is a good person for me to connect with. So I would recommend, anyone on here is welcome to, email me with any questions. Um, find someone that you can connect with that can guide you, and also find groups that I know, Rifat, you're on some of those groups. So finding groups to just, put a question out there is a really good way to start.
Great. Okay, so Sukarna Bonik, তোমার question answerটা হচ্ছে basically astronomy data গুলো archive পাওয়া যায়. It's available on online, so you guys can search it on Google and you guys can collect all the data from any kind of astronomical objects like supernova or planets or exoplanets. And Renuma Ryan is asking, how do you process basically deep sky images?
Yeah, the steps that I went through are really the key. The biggest thing is, when you start, the data is only as good as you have. They have this saying in computer science, right? Garbage in is garbage out, right? So the most important thing is collect good, clean data to begin with. And then the calibration steps that I went through in this presentation, those are needed to remove the things that aren't supposed to be there. So those are kind of the two major steps: data collection, data calibration, and then, following that, then you have, okay, here's the data, and then you can use other tools to remove, leftover noise or things like I mentioned. PixInsight is very, very powerful for that.
Okay, we have an interesting question from Faisal. How do you feel after discovering something new in the sky?
At first, I was not sure. I mean, when I first saw this thing, I thought that can't be something that hasn't been found before. Once it started to become clear to me, I contacted professionals and friends that are very serious in this. One of my good friends, he's on the East Coast, and he is well known in astronomy. He's been published by APOD, I don't know how many times. And so I reached out to him, and they're not professionals. He's not a professional astronomer, but he said, hey, maybe talk to this person. He might have. Once I realized that it had not been logged before, that nobody had noticed it or seen it, or it was just, it's hard to describe. I was just ecstatic. I was on cloud nine.
Well, আর কার কোনো questions আছে? তোমরা কিন্তু questions গুলো করতে পারো.
Yes, I have a question. Can you hear me, sir?
Yeah.
Yes, I can. Hello.
Okay. That if you use a regular DSLR in front of your telescope, on that case, can you get the same image like Takahashi, or why don't you use the regular DSLR?
That's an excellent question. In fact, before I bought the Astro CCD camera, I considered using a DSLR. The DSLR, the normal ones off the shelf, there's two issues with them. One is, the biggest one is they have a Bayer matrix. When you use a DSLR, you take a picture and you see color. Well, that color is not real because a CCD can only capture zeros and ones, right? It's just data. So it's monochrome. So they put what's called a Bayer matrix on there that has each of the pixels colored RGB, all the way across. And then they use color synthesis. So with that, it reduces, just to kind of cover it broadly, it reduces the sensitivity because you can be maybe not getting exact colors, for example. So that was one. The second one was DSLRs are not cooled. So you have a really hard time of doing the calibration steps because you cannot know exactly what the temperature of that CCD was. And so with that, now you're going to have problems when you subtract a dark frame because it's not going to match exactly the temperature of what the CCD was on the DSLR. So there's, those are kind of two major ones that I thought about. And like, okay, I'm going to get a cooled Astro CCD specific for astronomy camera instead of a DSLR, and then I'm going to learn how to use it. So because I didn't realize everything I was getting into, but those are kind of the main reasons. I hope that answers your question.
Okay.
Yes, sir. Thank you very much.
Well, Shukarna Bonig is saying, I just wanted to say that it's been an honor to be able to join this class. Thank you, Shukarna. Another question from Safrin, how we processed the image of a black hole, or kind of how the image of black hole was clicked. It's a good question.
Yeah. I know that, when I read about the actual, image of a black hole, that was using, terabytes or even petabytes of data. It was just a huge amount of data. So that's certainly not something that I'm going to get in my backyard, for example. I think if you happen to have a black hole in your field of view, that you wouldn't know it because the amount of data that you'd have to collect that would start to suggest that a black hole is there are just unimaginable. Because to identify black holes, they actually use movements of other objects, right? They see some jitter, if you will, in stars or other such objects that they didn't notice before. And so it's not like in the movies where, hey, the Disney movie, there's a black hole, you take a picture, it's this big hole that's black. They're not identified like that because these are masses that are supermassive, as you know, and they're somewhat invisible because they are pulling matter into them. And to be able to identify that on the scales that we're talking about is something you're not going to see. It's not like a river, flowing. It's like these scales are just humongous. And so if you can imagine, watching Earth, go around its orbit, you're not going to really notice it. If you're outside, it's going to seem like, oh, Earth is just kind of sitting there, or even the moon. You look in the sky, and so things, because of the scales and the types of matter and the physical processes that are happening, it's something that you need very specialized equipment and specialized analysis to identify those things.
Well, we have more questions from Sabia Sultana Bhim. How does the photos of space are collected by satellites?
Collected by satellites. So like there's dedicated space telescopes. Is that what they're referring to?
Sorry?
Because are they referring to dedicated space telescope like Hubble or something? Is that what they're referring to?
Acha. Sabiha, তুমি কোন satellites mean করছো? Yeah, maybe she is mentioning Hubble Space Telescope or something.
Okay.
Because
Yeah, and that's great because in fact I could bring it up, but I saved some backup slides on purpose. that talk about how does Hubble collect the data and calibrate data the same way I do. And not because I'm a special guy or anything, that's just the way it's done. Even with Hubble, Hubble's outside of the atmosphere, so it's very nice. They don't have to worry about weather like we do, right? Um, but the optics and the CCD all have the same issues that we do here when we're imaging from the ground. So they still have to go through the same calibration steps of, dark frames and even flats to remove optical artifacts.
Okay. This is the last question, I think, from Shanta Ferdin. Which celestial objects are the hardest to capture?
For me, distant galaxies. Um, Distant galaxies because there's one that's my favorite, and it doesn't even have a name. It's not like Andromeda or anything. Um, and in fact, I'm spacing bad pun there, but I'm forgetting the NGC designation. But it's one of my favorites. But it's very small, it's very distant, and it has a very cool structure. So I would say distant galaxies that are faint are the most difficult because you have to collect so much data. You have to, on this particular object, I collected, over a couple of nights. And there's some that I haven't even attempted some of those that would take, multiple nights or even weeks of data. So in my experience, the very distant, small field of view galaxies are because you need a long focal length telescope to bring those objects closer. The longer the focal length, the more difficult it is to have perfect tracking. And the telescope's going to be heavier too, so you better have a good mount. And so it just adds up. So the very distant small galaxies are the most difficult in my opinion.
How many asteroids have you discovered, except the emission nebula that you mentioned before? How many celestial objects have you discovered?
Just that one. And thank you for the question. There was an asteroid that I have an image of M33, and only 1 week before I picked the asteroid up, it was discovered by a professional government telescope. 1 week before I found it. And so I
Oh
was
wow,
looking,
that's unlucky.
yeah, so I barely missed it. And I contacted my friend that I talked about, who was my mentor. And he said, Jeff, I don't think that one's been discovered. I can't find it in the object database. So we checked and it's like, oh, wait, here it is. He said, they just found it last week. You just missed it. But it's kind of cool. If anyone's interested, please email me and I can send you a link to, I made a video. And so you can actually see this asteroid moving through M33's arms. It's of course in front, right? But it looks like it's moving through M33's arms. It's pretty cool.
Can you give your email to us once more? Because yeah, I missed the
Sure.
first time you gave it. Thank you.
I'll put it in the chat. Or can you do that for me, Rifat? Can you put my email in the chat?
Yeah, I'll do that definitely. No worries.
Awesome.
Okay,
And
and
please look there. Yeah.
okay, Tushi Shah is saying, love the class. Thank you, sir. We have learned something from you even, and everyone is praising for your class. And I believe this class is so inspirational and glad to have you again. And we are planning to do something on this image processing. We are gonna make another workshop on this if you do agree then.
Oh, awesome. Yeah, I would be happy to. I enjoy it.
Yeah. So thank you so much for your precious time again and again, and hope to see you soon. And let's take a photo. Why not, right? So please turn on
Sure.
your camera, everyone, and let's take a photo and capture this amazing moment. সবাই কাইন্ডলি তোমাদের ক্যামেরাগুলো অন করে একটু হাসি মুখে থাকো। বাকিরা ক্যামেরা কি অন করবে না? Oh, Aditya Dada, you are here. Hi. Okay, so
Hello.
our next instructor already চলে এসেছে. So we have our
Oh.
another instructor, Aditya Kar, who is a researcher on black hole and general relativity, artificial intelligence, and so on. Okay. আচ্ছা এই ভাই
Nice.
তোদের ক্যামেরা অন করতে কি সমস্যা হয়? হ্যাঁ, দাদা কিছু বলছেন? ওকে। বাকি যারা আছো তোমাদের ছাড়াই তাহলে আমরা ছবি তুলে নিচ্ছি। তোমরা মিস করলা তাহলে, ওকে? ওকে, আচ্ছা আচ্ছা কয়েকজন বলতেছে একটু ওয়েট। ওকে, we are waiting. No worries. What's the time in your zone, Zev?
3 a.m. So
Oh
I'm
my
ready
God,
for
it's
sleep.
it's midnight. Okay, so you're gonna
So
sleep
if I
now.
look tired, yeah, if I look
Yeah.
tired, it's because I am tired.
Okay, so let's take a selfie. সবাই একটু হাসো টাসো। Okay, thank you so much, my friend, and hope to see you soon again. Take care and all the best.
Thank you so much, Rifat, and everybody. I really appreciate it. It was great. And
Thank
hope
you.
to see you all again. Bye-bye.
ওকে, দাদা আপনার সেশন শুরু করার আগে আমরা একটু 10 মিনিটের ব্রেক দিব।
হ্যাঁ, নিশ্চয়ই শিওর।
এন্ড হচ্ছে আমরা একটা অ্যাটেন্ডেন্স নিয়ে নিব। তোমরা যারা যারা আছো ক্যান্ডি কেউ লিভ নিও না। ওয়াসি, ইউ ক্যান স্টার্ট ইউর ওয়ার্ক।
ওকে, আপনারা যারা যারা আছেন, যাদের নাম ধরে রাখবো তারা প্লিজ রেসপন্স করবেন। ওকে, okay, I'm gonna start now. Shukorna Bonik, are you present?
Yes, present.
Okay, Ahsanul Azim. Ahsanul Azim. Okay, Sabiha Shabnam, are you there?
Present, Bhaiya.
All right. Tahsima Mim.
Yes, present.
Shangskriti Shaha.
Present, Bhaiya.
Ishtiaq Ahmed.
Present, Bhaiya.
Khadija Rubayat.
Present, Bhaiya.
Arnab Pandey. Arnab, are you there?
আচ্ছা, অর্ণব আমাকে বলেছে ওর
He
মেবি
was
ক্লাস
here.
আছে। ইয়া, ক্লাস আছে ওর, ও মিউট করে রাখছে আই থিংক। সো টেক হিজ অ্যাটেন্ডেন্স।
Okay, Parthiv Paul.
Present, Bhaiya.
Okay, MD Murad Islam Mahin. Mahin, are you there? Okay, next, Promit De Sarkar Arjun. Promit De Sarkar Arjun. Okay, next, Troy Mitra.
Yeah, I'm here.
Okay, Purnona Isat Mithila.
Present, Bhaiya.
Okay, Sumaya Parvin Kanis.
Present, Bhaiya.
Tanu Shaha. Tanu Shaha. Okay, you're here. Sumaya Nagari. Sumaya Nagari. Okay, Soed Tamzid Tazwar.
Present, Bhaiya.
Okay, Rehnuma Ryan.
Present.
Chris Rosario. Chris Rosario. Hafsa Fariha.
Present.
Okay, Rafid Rahman.
Present, Bhaiya.
Okay, Safrin Moon.
Present.
All right, Alamin.
Present,
Alamin.
Bhaiya.
Okay, Abdul Ahad Sani.
Present ভাইয়া।
Okay, Hasin Tahsir Farbi. Hasin Tahsir Farbi. Okay, next Shayantan Fardin Nobi. Shayantan Fardin Nobi.
Present ভাইয়া।
All right. Suhala Nagari. Suhala Nagari. Next Arafat Rahman Orko.
Yeah, present.
All right. MD Javed Nahian Ratu. MD Javed Nahian Ratu. Okay, next Al Mehdi Hassan.
Yes, I am present.
Okay, MD Ridwanul Kibria. MD Ridwanul Kibria. Okay, next Tawfiq Islam. Tawfiq Islam.
Present ভাইয়া।
Okay, were you absent the previous 2 days?
Yeah, because I forget the date and I was and my class was at that moment, okay? For the reason I cannot attend. I couldn't attend.
Okay, okay. Can you please tell
I
me
missed
from which district you are from?
from Rajshahi, and my misfortune that I missed those classes of yesterday's.
Okay, next Naim Ferdowsi Aishi. Naim Ferdowsi Aishi. Okay, next Sabiha Sultana Mim.
Present ভাইয়া।
Okay, next Tanzila Nahian Nisi.
Present ভাইয়া।
Okay, next Ryan Khaled Navid. Ryan Khaled Navid. Okay, next MD Faisal Kobir.
Yes, I'm in here.
Okay, next Shinjoy Dhar.
Present ভাইয়া।
Okay, next Junaid Nabib Alwasi.
ভাইয়া present।
Okay, next Arafat Kabir.
Present ভাইয়া।
Okay, Tasnim Rahman Naushin. Tasnim Rahman Naushin. Naushin, are you there? Okay, I think she's absent. Okay, that's all for today. If you have missed your attendance, you can inform me now.
ওয়াসি তুমি একটা কাজ করতে পারো যে লিস্টটা দেখে দেখে ইউ ক্যান চেক দ্যাট আউট যে কে কে হয়তো মাইকে প্রবলেম থাকতে পারে অর ইন্টারনেট প্রবলেম। তুমি
Okay, okay,
লিস্টটা
I-
দেখে চেক করতে পারো। আর যদি
হ্যালো ভাইয়া।
হুম হুম হুম।
জি, আমি ভেবেছি 3-4টা থেকে ক্লাস হবে, তো তাই আমি ওই জেফ্রে জনসনের ক্লাসটি করতে পারিনি, অ্যাটেন্ডেন্সও দিতে পারিনি।
আপনি গত 2টা ক্লাসও মনে করেননি, 2 দিনও একদিনও ছিলেন না।
জি জি জি, প্রবলেম ছিল, ঢাকা ছিলাম আমি।
ওকে, সো যদি কেউ মিস করে থাকেন অ্যাটেন্ডেন্স কাইন্ডলি চ্যাট বক্সে জানান, তাহলে ওয়াসি সেগুলো নোট ডাউন করে ফেলবে। এন্ড let's go to the next class, and Wasi, you can stop this recording and you can start again, right?
Yes, okay.